Too. Welcome everybody to the 10th colloquium this semester. We've really come a long way, so it's really awesome. And today we're really excited to have Dr. Gagan Agarwal. Am I saying it right?
Yeah, close enough.
Yeah. Who is actually a new professor to Gus University in the School of Computer Cyber Sciences, but not a necessarily new professor. So he's came in as a full professor, and he's been has a long career since 1991, where he got his master's and PhD degree from Maryland in College Park, which is a really good school. Nowadays, their computer science department is huge, getting bigger. It's actually the #1 major in their school.
Yes, I know that. Yes.
Yeah, it's pretty cool. But the other people here might not know that. So he's published lots of things, up to 275 papers, doing work in high performance computing, parallel machine learning, data mining, cloud, edge computing, scientific data management. He's done lots of really great stuff in the research community, and even his dissertation was awarded by the ACM. He served, sorry.
Yeah, I've served on that now.
Served on the dissertation award committee. Yeah, my bad. So a lot of accomplishments, and so we're really lucky to have him here with us at Augusta University. And today he's going to be talking about achieving performance and programmability for data-intensive applications with production-based APIs.
Okay.
So thank you.
Thanks a lot, Harley, and thanks for everyone who's here. Feel free to stop me. I don't know, maybe you've been muted, but if you're not going to be too noisy, maybe unmute yourself and then, feel free to ask any questions. I like it quite interactive. So the high-level theme here is, besides the long title, that when a high-performance computing person started looking at some of the big data solutions that existed and that are still, very, very big in the industry, what they kind of, did to try and come up with, maybe propose some better solutions. So the background here is, well, some of you might have heard of MapReduce, Hadoop, Spark kind of things. Otherwise, I will try to give a very, very quick overview. But basically, these things started in Google around 2003, 2004 with the data center. So they started saying that, well, we have a lot of data. We like to do analytics on this data. And that analytics, because the data sets are so large, we will like them to be very efficient, make use of parallel capacities in a data center, and what should be done to try and achieve that. So that's where they came up with MapReduce, which has since then seen a lot of work and a lot of variants and a big presence in industry. So a lot of the data center level analytics gets done in using MapReduce or its descendants, or you could say as part, some version of things in the MapReduce ecosystem. So what is MapReduce? Well, MapReduce is simply saying that a lot of applications can be parallelized with a very simple API comprising of a map function and a reduce function. And here, what we are doing here is let's say, we have 3 records and we want to calculate, in this example, the frequency of occurrence of different letters. So this is a very, very, obviously a simple thing. In almost any programming language, you can write a very small piece of code to do that. But let's say that we want to get efficiency. And again, when you have 3 records, parallelism is not going to help you. But when you have, 3 billion or a much higher number of records, then parallelism helps you. So let's say we split these up into 3 different sets of records. And then we are going to apply what is called a map function. And the map function is going to process a record like XBB. And it's going to say that, well, I have seen 1 occurrence of X, 1 occurrence of B, 1 occurrence of B. And in parallel, you will go through CBA and note that you have seen 1 occurrence of C, 1 occurrence of B, 1 occurrence of A, and XAC, you will do something similar. Now you can try to look into potentially combining them and go through a couple of steps, and ultimately you will come up with, so once you have generated what are called these key value pairs, X, I've seen one occurrence of, the map phase is done, then you get into combine and reduce phases, and ultimately we'll come up with the obvious answer. Now, the beauty of this, which maybe trying to fit any example in one slide might be hard to really establish, is that parallelism can be achieved with a really simple API. In fact, MapReduce API has been taught at Berkeley in their intro programming class, because they felt that you don't need to wait till advanced electives and so on to do that. So there have been many systems. In fact, Hadoop was an open source system that tried duplicating Google's internal MapReduce implementation, though wasn't quite as efficient. And then Spark and many systems have come out. So Spark, in fact, is a system that is quite widely used and is has replaced Hadoop in most places. And it goes beyond MapReduce, but follows the similar idea of saying that a lot of parallelism can be done with simple abstractions that are easy to use. And not everything that can be parallelized using them, but a lot of things can be. So Spark, again, extremely popular, and it, besides MapReduce, uses some other functions, group by key. There is a distinction between map and flat map, reduce by key, map values, sample, union, so on, sort by key. And another big thing about Spark is that it kind of expects a lot of memory to be available, but also then tries to make things resilient. So very big data centers from the start of Google work, they have felt that large data centers, especially built using commodity components, it's very likely that something would fail. So if you have 1,000 machines and your job runs for several hours, then it's almost expected that not all 1,000 machines will be up and running all throughout. And these failures can, if you're not careful, they can, let's say if a job runs for 6 hours and after 5 hours, one of the 1,000 machine fails, if you're not careful, you might completely lose all the work. And what Hadoop and Spark have tried doing is to make sure that you have maybe at worst some kind of a graceful performance degradation remaining with the remaining machines. You continue, you rebalance the work, you do not lose what you have already done, and you get your results, maybe in a slightly slower fashion. So the big thing that MapReduce and Spark have achieved is what we like to say programmability or parallel programmability. What that says is that we want to make things easier to program. And clearly, if you look at the other alternatives for parallel programming, things like MPI and even some of the parallel programming languages and OpenMP, they have been relative. They have been more general, but they have been harder to learn and program with, and you are more error prone as a programmer doing that. And as I said previously, this can be seen with Berkeley even talking about MapReduce in their intro programming class. If you can write some Python programs, you can parallelize them using Python too. But what about performance? And some people, including myself, we have done some comparisons, and we have shown that if you really, on the same number of machines, you're trying to compare performance, all this MapReduce work has been very slow. And I will show you some results. Now, high performance computing right now, really there is one dominant programming framework that 80 or 90% of the programmers are going to use, that is message passing interface. And that also has its own ecosystem. In the HPC community, which is not as big as the data center community right now, but they have entirely focused on performance. And the wisdom that has emerged is that, well, choose one. I mean, you can't have everything in life. If you want to get really good performance, okay, use something like MPI and then tough it out. And, MPI usually is done with C and C++ with explicit memory management and explicit memory passing, message passing. And if you want a little easier things, for example, within Spark, you can work with Python or its variants like Scala. And, life is easier, but you're not going to get performance. So our work has been driven with this goal that, well, can we do both? Can we get performance by tweaking around the APIs and implementation just a little bit and get programmability? Also because we are using a relatively simple API. So what we have shown at a very, very high level, you can say that if you can tweak your MapReduce API, and then you combine it with some amount of care in performance, in your implementation of the system, not the program written using these, but you build your systems which try to support this API, then you can actually do really both. So I'm going to talk about 3 different systems that over years with various graduate students at Ohio State we built. So first one is called SMART, which does in-situ data analysis. Then the second one is Smart Streaming, which does fault-tolerant online processing. And then I'll talk about very new work that appeared in a conference just the past summer, which is now mapping applications to a hierarchy of multi-core devices. And this evolves, well beyond MapReduce, but you will see the basic ideas. So the key to our work is what we call a reduction object-based API, which starts with a function that is very similar to map, or at least partly resembles map. It's called generate key. So earlier with MapReduce, I was showing how you're getting things like X and 1, and that X, you can think of it as a key. So we generate a key. But then we are going to do what is called an accumulate, which means that we do not generate a key value pair, but rather do a reduction right away. And then we can do things like merge and post combines as needed. So if we walk through an example, let's say that you are again getting these letters and then you're trying to count the frequency of their occurrence. Well, you will, with MapReduce, you will be generating these pairs that I have seen an occurrence of A, and that's one occurrence, so that's A1, and so on. Here you will be doing accumulation as you go along, which means that starting with an initialized value that I have seen 0 occurrences of A so far, you're going to do this accumulation on the key and directly know that, okay, I have seen 2 occurrences of A. And in parallel, someone else could be working and maybe they see 1 occurrence of A, and later you can merge them together and say that, well, together we have seen 3 occurrences of A. Now, again, examples in this domain that you can fit into your slides are probably don't do justice to what is being achieved. But if you go back and compare it with MapReduce, well, we were really taking a lot of memory generating these pairs that I have seen 1 occurrence of A, 1 occurrence of A, and another occurrence of A, and so on. And in replacing that is a single representation saying that, well, on this machine, I have seen 2 occurrences of A. And that turns out to be quite important in achieving performance, as I will show. So again, you can start combining across different threads and then across different machines, and you can come up with the same results that you would have gotten with MapReduce. So this API that we proposed, actually, we have sort of a history behind that. We did it before MapReduce, published a couple of papers, didn't really, get all that much of attention. And then MapReduce came up, Google came up with MapReduce couple of years after that. And, Hadoop became an open source implementation that everyone was using. And then we kind of had to go back and say, but, isn't our API a little better? So we have continued to build some systems using that. So if you think about programmability, now I will admit that clearly we have lost something. And the thing that we have lost is that MapReduce is supposed to be a functional idea. And everything is state free, you might say. Here, programmer needs to declare this reduction object, initialize it, and there is a state being maintained. That state actually turns out, I'll not talk about in this work, but it turns out to be actually helpful in providing fault tolerance in ways that is more efficient than at least what Hadoop had done. That has been a separate line of work we have done. But apart from that, we get fewer lines of code. We are not going back to anything similar to MPI programming. And our claim is that even some of the MapReduce code one could start with and modify it. So, okay, this is a very, let me skip it, but this is a little comparison of the code and between the MapReduce API and the reduction object API, and it's probably not readable, but the amount of code you're writing is actually quite small. It's actually even smaller than MapReduce. And well, yes, I mean, you need to be a little bit more careful. You lost the functional state-free kind of properties, but you get much better performance, I will show. The big thing here is that, so this is the comparison that, you're generating a lot of key value pairs. And in fact, for some data mining applications, you finish up having a lot more values than, you finish up having an intermediate output of almost the same size as the input you're processing. And obviously that's going to cause a lot of issues in your system. Those memory pressures start hurting performance, and it also impacts where you can even do this work. Now, we also came up with, I think in the interest of time, I'll not get deeper into it, but we also came up with an MR-like API. We modified reduction object to try and take it a little closer to MR-like. And let's just maybe skip details of that. The differences are kind of subtle. So, let's just say that we have played around quite a bit with this API business. So here is a little comparison. Now, before you jump at me and kind of point it out, programmability is probably an extremely hard thing to measure. I mean, how do we say that something is easier to program in than others? And one used but flawed metric for that is lines of code. Okay. Maybe you can write something in Python using a lot fewer lines of code than assembly, and that tells you that Python is easier to program than assembly. I do not fully buy it, but still use it. Okay. So with that caveat, in the absence of anything better, let's just do a little comparison of 4 applications and the lines of code. So MapReduce API, reduction object API, and our variant, well, we find that we are actually writing fewer lines of code. And, we could have compared with things like MPI, which would require much more direct communication and a lot more effort in getting it right. So now, having said this, let's talk about a series of systems that we have built over time using this API. So the first one is for what is in high performance computing called in-situ data analysis. So what is in-situ data analysis? The context is that you have a big high performance computing machine, big, and it's running a simulation. So a simulation is typically written in some parallel language like MPI, and it's out there running, and it typically generates or can generate a lot of data. So as you're trying to simulate a phenomena, your kind of the values in your big grid continue to evolve, and people like to output them and analyze them and see what's happening. So the in-situ analytics means that, well, the over time high performance computing machines have increased computational power, and the memory and the IO have not kept speed with that. So now if you took a simulation and the output that you were producing, and let's say that, you increase your resolution, you try and increase the computation and put it on a modern machine, the IO is going to become a bottleneck. So, your computation might be 100 times faster, but your IO is only maybe 3 times faster. And that has motivated in-situ data analytics. So we used our API and our idea to build a system for doing in-situ data analytics. And most of the in-situ data analytics people had written their own, C programs with explicit message passing with MPI. So we said that, okay, can we take something from the MapReduce world and simplify in-situ programming? So now if you just say that, okay, I want to take MapReduce idea and apply it to in-situ, I mean, clearly, Google did not design MapReduce for that. And there are many, many issues, but one of the biggest one is that there is a big memory constraint mismatch. I mean, as I was showing you with these key value pairs, the big assumption in this data centers is that, well, memory is kind of, you can buy more memory. You can have servers with, 512 gigabytes or even a terabyte of memory, maybe by today, even something a little higher. So when you can do that, well, I mean, what's really the big issue trying to save memory? Now, in in-situ data analytics, no one will buy that. There is plenty of memory argument because these machines are memory constrained. The data sizes or the grid sizes used in HPC are usually pretty close to the memory capacity, which means that you want to do in-situ data analytics, but while using a very small amount of memory. Then there are some other issues that, we probably don't need to get a whole lot into. Scientific simulation is using a parallel programming view, and MapReduce tends to have, is hiding all the details of data partitioning and all that from you. So that's something that, maybe is without a lot of background in both the domains is a little hard to appreciate. But, we address that. That's the high level takeaway. So the memory constraint mismatch, as I was talking about, is that MapReduce, by its basic definition, it produces a lot of intermediate data. Sometimes you also need to do a sorting, shuffling, and grouping of that data. This can all be very expensive. And really, in in-situ area, you're not going to have a space to do that. So to build this, we built this system, which is doing MapReduce style processing. Really from scratch. We didn't take any implementation of Spark or anything. We built it from scratch. It's implemented in C++, and it uses OpenMP and MPI on the back end. It does not really require the application developer to use them. So the API I have already talked about. Okay, why am I repeating these slides? Okay. Let's go into the in-situ modes and what we do about that. So besides using the more efficient API for to avoid any intermediate results, we also support different ways in which in-situ analytics might work. So the idea is that the simulation is running on a large number of nodes. So those are connected with message passing with each other, but every node has a number of cores or threads. I mean, there could be more threads than cores, and that's kind of a long story by itself when that makes sense or not. But let's say that you have many cores and many threads. Now, there is two ways that the simulation program can be sharing resources with the in-situ analytics program. You could be doing a what is called a time sharing mode, where you run your simulation for a number of time steps, then shift over to the data analytics part, And in that case, you need to worry about, how you're going to really, communicate the data, make sure that, whatever is produced, make sure that we are not doing a lot of copies of the data that we need to analyze. And then we can have a space sharing mode where we basically have some number of cores dedicated to in-situ analytics and others to simulation. And then again, the key thing that we worry about is that how do we avoid making unnecessary copies of data. So we do all of that. We build the system. I'll not get into a lot of details of it, but we partition the input to the in-situ analytics, which is the output from scientific simulation. We put it in many partitions. We further break it into blocks, and then basically we are creating reduction map, combination map. So this is more or less map reduce like processing that is happening with our API, and is quite fast and very memory efficient. So the system was built. Some other engineering aspects of it. We focused quite a bit on ease of use, because someone who is using a simulation program wants to be able to link the two together. And again, I had talked about being able to take the sort of internal data that is kind of coming out of a simulation program and be able to analyze it without having the simulation writing it or even making a copy. So we worry about all those issues. We make it really easy to link the in-situ program together with the simulation program. So I'll skip some of the details on these slides, but that's the main idea, that
again,
just
can I ask you a question?
Yes, please.
I'm sorry, can you come back to the system overview, like 2 slides ago?
Yes.
Yeah, this one. So maybe it's a naive question, but at some point earlier on, you said that the splitting and reduction could be made either across threads or across machines. Is this a distinction that you can see in your system, or are you just agnostic and saying, well, I don't know, those may be threads, those may be machines, I don't care about that? Or do you have a way?
No. Internally, you do need to care about. You don't want the user to be too cared about it, too bothered about that. But the system needs to worry about. So basically, I mean, the way any high performance computing machine today is that it has many nodes. And every node, if it is sort of like your, I mean, maybe a little advanced version of your desktop, then it has somewhere between 8 to 28 cores, maybe across a couple of sockets. And typically you're going to run some concurrent threads to manage that, to make use of that parallelism. And then you do something else across the machines, because those machines then are not sharing the same address space.
Yeah, okay. But so do you have like 2 splitting operation? Do you have splitting across thread and splitting across machine, or you just let the machine deal with that and that's just a different procedure?
So the in-situ program is written without any, the user is writing in-situ logic, what they want to be analyzed out of the data without having to think about any of
it. Okay, thank you.
Okay, so to show you some results, so here, the first thing we will just look into is scalability of our system. So let's say it's the same amount of data, but that could be coming out of simulation running on 4 nodes or 8 nodes, 16 nodes or 32 nodes. And then you analyze it again using the same number of nodes, and how well does it scale. So we have done this with about 7 or 8 kind of popular analytics kernels, k-means clustering, kernel density estimation. And you can see that, as you go from 4 to 32 nodes, your execution times decreases more or less linearly. So that's a pretty good thing, that, the system continues to scale. That's always a good test when you are in this business. So now we look into another aspect, which is that you have the same number of nodes, 64 nodes, but you increase the number of threads. And are we still able to scale them? Yes, we are able to. So again, we are going from 1 thread per node to 8 threads per node. And we are, I mean, not necessarily 8 times, but we are by a reasonable margin running faster. Now, we did this comparison with Spark, which is this popular system. Spark is an implementation of MapReduce with some other functions thrown in. It's really big in industry. And now, again, Spark was not meant for in-situ analytics to share resources with a scientific simulation, but we tried to be fair to them and try to fit it in and make it work together. Spark, as I said, has a couple of big issues. It requires a lot of memory. It's usually, the system itself is written in a language called Scala, and then the user program on top of that is also, written in Scala. So in multiple ways, it's quite slow, and we are, outperforming it for these 2 applications by, factor of 62 or 92. So it's really almost 2 orders of magnitude. We are running faster with various design choices and better engineering. So we have many explanations for why those results are. I mean, in certain communities, Spark is worshipped, so it's always, you have to be very, very careful. But just to highlight another thing, so we did not really, have Spark work together with a real scientific simulation. We had a dummy program, not really consuming resources, but just, producing data. And Spark took about 90% of the 12 gigabyte memory, which means that on each node, which means that, if it was to share resources with an actual scientific simulation, I mean, there is no way you can make it run there. And our system required about 16 megabyte on top of half a gigabyte of memory that actually had to be analyzed. So now we have said that, okay, this is our claim because there aren't really good metrics for programmability, but we claim that, well, our programmability is still pretty good. Performance is much better. How do we compare with systems that we claim are harder to program, but are really geared towards performance? Is our performance getting quite, and how does the programmability compare? So we created a scenario where we implemented the same analytics functions using MPI. So this is doing explicit message passing, actually MPI plus OpenMP. MPI is used across nodes, and OpenMP is between the node, within each node. And here you can see that we are slightly slower, but not really by much. And if you again believe number of lines of code as a metric, we are actually eliminating a lot of the lines of code from MPI. So we have both programmability and performance. So let's, I've already used 40 minutes and I do plan to finish at 1:55. Let me talk about the couple of other systems. So we have also built a fault tolerant stream processing system. So, in Spark has been sort of evolved into a Spark streaming system, and we have tried to go into that space also. This is just a little background that maybe is not very important. Kafka is a sort of a program that generates these streams and is used in evaluating all the systems. So we interface with that. Now we have this little scheduler and overall system design. And it's not really that different from the previous system, because in the previous system, your stream of data was coming from a scientific simulation that was running. Here it's coming from an outside store. We pay more attention to fault tolerance, which is something we did not really do in the work that I had previously shown you. We try and achieve fault tolerance and then see how we compare with Spark. So our API is still the same. Fault tolerance, because internally we are using OpenMP and MPI. There are some big issues, many design decisions. Our paper talks about it in quite a bit of detail. I think I will, just kind of skip past those details, but they are quite interesting. And again, MPI is a system not really known for fault tolerance. So the big story here was trying to build a fault tolerant system on top of MPI. And I think, the audience that knows MPI, there is quite a bit to talk about, probably not so much here. So I think I will again, skip past these details. Here is the whole, setup for evaluation. And, again, we set it up, several different applications in streaming scenario. And and what we did was we did a throughput comparison with Spark streaming and another streaming system called Flink. And then we also looked into the behavior when one worker goes down, and we compare it with Spark. Flink, as far as we know, or at least at the time of writing that paper, was not fault tolerant. So we compare against Spark and see what is going on. So throughput, you can see, we are doing much better. So the measurement here is MB per second that you are able to process on 32 cores, 64 cores, 128 and 126 cores. You can see that they increase, and the other systems are much slower. So this is logarithmic scale. We are 10 times or more faster than other systems. Your orange lines are Spark, your Flink is the gray line. And that's pretty much the story across all 4 applications. We tried evaluating fault tolerance by creating a scenario where one worker goes down and looking into how these systems degrade. Degrade in the sense that, how much throughput is lost. And because maybe our system is quite efficient when there is, there are no failures, as a percentage of, the resources lost. So, for example, with 256 cores, and I think this is because of some amount of replication that's going on in Spark, they don't really lose that much of performance. They lose maybe 5% of their throughput. We lose a little bit more. And that has to do with some of the strangeness with partitioning for this particular application. But when you go to, let's say, or when you have only 32 cores and one of them goes down, then we are quite comparable. Again, as I showed you, this is a performance degradation shown relative to the performance without any failures. So if they are much slower, even after losing one core, they will lose 25% of their throughput, and they will still be much slower. We just happen to be in many cases losing, in at least several of the cases, losing a little higher fraction of our throughput, which was much higher to start off. And there's some explanations for it. At some level, it's getting into some strangeness of how partitioning works. And if you are very efficient in your base case, then you tend to lose a bit more. So, again, I've quickly glanced over this system. Maybe I want to spend a bit more time on the last system. That's our newest work. So let's jump to this work, because I'm kind of excited about the kind of configurations that are emerging. This is a little bit getting outside of the traditional HPC. So this work is titled A Pattern-Based API for Mapping Applications to a Hierarchy of Multi-Core Devices. And the idea is that we are seeing emergence of Internet of Things. We are seeing emergence of what is called edge computing and fog computing and so on. And what we're really seeing is many devices that are out there and can collect some data. These IoT devices could be, they're typically much smaller than, your traditional, desktops or laptops. They have slower clock frequency, memory size, cache size, but they're still fairly complex systems. They are increasingly having multiple cores, things like Raspberry Pis. And what you can see is an environment emerging where you have a large number of such devices that could be collecting some data. They might be collecting some pictures and trying to analyze it. And they are backed by your traditional computers. Maybe for several Raspberry Pis, you have one or two machines and real machines and maybe a backup of on the cloud. And you want to do data processing, maybe real-time processing used in this environment. So what we wanted to do in this work is to extend our reduction object API to broader types of applications, and we will add some more functions. We will focus into parallelizing not just on our desktop, but also on some smaller devices. Raspberry Pis, the ones we worked with, had 4 cores. And we want to also split the work between the processing that can happen on on the devices that are close to data collection, and the processing that happens at the back end with the overall goal of trying to keep the latency low. So the applications that we looked into this work, the previous 2 applications had looked at some of the standard analytics, data mining kind of kernels. What we look at here are some of the computer vision applications, and they have their own style of processing. You typically try to do a lot of sliding windows on an image and try and find certain patterns. So you might be searching for certain types of grids in a 2D sliding window. And 2D sliding window means that, well, if this window is, let's say, 16 by 16, and your image is 256 by 256, you will start in one corner, and then you will repeatedly, maybe, just by an offset of 1 or sometimes a little higher offset, you will slide it, keep sliding in both the directions, separately in different directions, and you will apply this window. So a lot of the processing here follows this style. What it does is usually a feature selection. So you are looking for maybe presence of certain edges, certain lines, some rectangular features, and you keep sliding it and keep looking for it. And there are some frameworks like OpenCV that have traditionally been used for building them. You do what is called cascaded detection, which means that maybe you do a certain test, and if that's not true, you apply something. At some point, you might just say that I don't need to do any more tests. So keeping that in mind, we extended our reduction object API by having gen key accumulate and merge, but also an explicit notion of windows, pyramids, and convolutions. So again, this is a paper that has all the details. I cannot really, capture everything, but the idea was that with a pattern-based API, we are able to write fairly complex computer vision applications and parallelize them both within the Raspberry Pi and using the cores on the regular machine, and also split the work between the two. So the notion of pyramid is that normally when you start with an image and when you are applying these little filters, these filters are of fixed size, but you're going to keep down sample or downscaling your image, and you will try to apply these filters there. So if you're looking for, you have a large high resolution image and you're looking for a 16 by 16 filter, maybe you will not find it in the original image because you're looking for certain line or maybe you're looking for human eyes. But as you keep downscaling it, if your resolution is too high, then you might find it at a lower resolution. So this is the idea of pyramid processing that is very common in computer vision applications. And we try and exploit that to break the work between multiple devices. We do several optimizations, reusing partial results. So again, a lot of details are specific to these computer vision algorithms. But let's again jump to the results. As you have probably seen, I like to show you these figures, but that's kind of common in experimental systems. So here are 3 popular vision applications. And what we are showing here is a comparison of our system, which is using the pattern-based API and parallelizing also using that. And comparing it with the sort of the state-of-the-art implementation, OpenCV based, which also parallelizes using its own ways, but it's much more complex code and it has been around and optimized. And you can see that our execution times are somewhere, we are definitely saving quite a bit of time, somewhere between 40 to 60% reduction in execution time we are getting. Another way you can look at it is that both the systems continue to scale. So on the top part, we have results on a regular machine, has up to 16 cores. And then in the bottom part, we have the Raspberry Pi, so that has only 4 cores. The normal execution times are quite large on the Raspberry Pi because it's a slower machine, but we continue to outperform this system, the existing system, and then also continue to scale well. We also looked into distributing the work between the Raspberry Pis and a desktop, and we find the right split point, and we are able to reduce performance by doing that. So overall, again, we have shown that this pattern-based API, including our reduction object, but combining some other aspects from this, they can be helpful for these computer vision applications, and especially in what is emerging as a theme for processing, in the sense that we will have a lot of data collection using IoT devices. IoT devices will continue to get more powerful for data collection or for data processing also, but not quite the same way as your desktops and your cloud. And that's something that that's an environment that for which really there is very little work on application development. And our pattern-based API is specialized for computer vision, but is a start. So that's sort of, all, I wanted to say. We can achieve performance and programmability, and this reduction-based API generalized into pattern based reductions. They enable some interesting optimizations, and especially with this latest work on this Raspberry Pis and backed off by this, I think we can continue to consider more applications and extend this. So it's 1:55. We have time for questions. I hope there are some questions.
Okay, well, thank you so much, Gagan. Thank you for staying on time too. Indeed, we do have time for questions. So you can monitor the chat, or you can unmute yourself to have them directly.
Right, and just speak up. I mean, I'm happy to just make sure that you mute yourselves. And
okay, so maybe while they're still thinking about it, I have a small question.
Okay.
I really enjoyed your idea of saying, okay, there's a balance between performance and ease of use. And getting both is really quite impressive, I must admit. I mean, getting at the same time smaller lines of code and better performance is really quite an achievement. I'm not familiar with HPC. I just know a tiny bit of OpenMP.
Okay.
And that's one thing I really enjoyed in OpenMP, that you don't need to change your source code to use it, at least on the surface of it. You just need to put kind of annotations in your source code. You just kind of put flags saying, well, OpenMP,
right.
Can you try to do better on this part? And well, okay, you have to be careful because sometimes OpenMP will messes up everything. Sometimes it will actually work. but
Right.
you don't need to change your source code at all.
Right.
How much or how little can you do that? Like imagine I come up with some code that is not optimized for parallel distribution at all. And I
Right.
say, hey, again, can you do something with that? How much
Okay,
do you
yeah, so that's a good point.
or can you just kind of just tweak some parts and
Right. Yes. Yes. Okay. So I think I understood the question. So where does normally we have been focused on distributed memory where kind of MapReduce is one end, which is high programmability, high ease of use, lower performance, and MPI, which is on the opposite spectrum. Now, what is OpenMP's place? So, first of all, it's shared memory only, which means, there are fewer things you can do with it. If things can happen in that. OpenMP is, yes, I mean, I think people find it quite easy to use. That's really not the issue. Getting good performance from OpenMP has been a mixed bag for people. So in fact, a lot of the sort of, you could say, I mean, professional HPC programmers, people who are dedicating their life to running one simulation program, efficiently for last 10 years or something like that. I mean, DOE labs tend to have a bunch of those. They often finish up splitting the work between MPI processes even within one node.
Okay.
Because they are saying that, okay, I need to use OpenMP or MPI anyway. And if I try to use OpenMP within one node, I tend to lose performance. Okay. So, I might as well explicitly split things between threads, which in fact is more work and also is, doing some strange things like, now different processes are kind of sending messages from each other when they should be, just able to share some buffers. So yeah, I mean, that's OpenMP is kind of a, I mean, it's a good point you're making that, yes, I mean, you can't really complain about programming difficulty with OpenMP. I mean, it does for what it works for, it works quite nicely. And I don't think you can really improve OpenMP. I mean, if you are in shared memory space, you can't really improve on OpenMP for programmability.
Okay, and so I kind of have a follow-up question. What do you use it for? You said that's, if I remember correctly, your second tool was actually built on top of OpenMP.
Okay, right. So, well, I mean, so internally, when we are splitting the work between many threads, we have in some cases used OpenMP.
Okay.
But we hide it from programmers. And now, we could have done MPI threads, we could have done regular threads. I mean, I think this is just a decision we made.
Yeah, okay. Okay, but so you use it mainly to not to have to deal with the bureaucracy of creating and splitting the threads yourself. So at OpenMP just deal with the thread creation.
Right.
Okay. Okay. I may have another question if nobody has anything. So the other thing I was curious about is, so if I understand correctly, the third development that you showed us was kind of to get a gradation between IoT, desktop, and cloud, saying, okay, if I want to run a process on an IoT or handheld device, and at some point I exhaust the memory, then I need to be able to kind of bend some of the workload to the higher level and to kind of do that as many times as needed.
Right.
And my question is kind of a follow-up on the one I asked you during your presentation is, in this system, would you make a difference between local threads and threads that you send to other machines? Or you're just saying, well, I'm just creating threads, and when I'm kind of having an overflow of thread, I'm just going to shift some to some other place. I'm just going to send them to some other place. Or do you have a much more...
Okay, I think I get your question. So I mean, so what you described is not what we are doing.
Okay.
And let me broadly say that really splitting the workload between maybe multiple cores in a smaller IoT device, and then, something on the cloud side is in general a very hard problem because, it's just, these are threads with different capabilities with a big sort of, limited latency and maybe even a little bit of, failure proneness of the communication and everything. Now, in our work, which has just considered computer vision applications, I was showing you this pyramid, and we are kind of exploiting that pyramid to try and achieve a little balance between the IoT device and the back end, which would be a more powerful machine. And we are saying that, okay, because concurrently you have to apply the same filter on several levels of downscaling, that could be a basis for splitting the work. Now, this is very specific to computer vision applications. We have done some work in other contexts in the same setting on some other applications, actually like convolution neural networks. And there you have many layers, and you can do some partitioning that, first few layers can go on the IoT devices, and then the others could go, on the other side. But in general, can we have an answer to how you go about splitting the work? Not really, because not every application is like a computer vision application, or these layers of a neural network.
Okay, and so is this one of the reasons why you started working on computer vision? Was it because it was kind of easy to start applying your methods because of that pyramid vision?
No, not really. This was, I think we were looking for, there were, so about 2 years back with 2 students, I thought of getting into a little bit of this IoT and so on. Okay. And there's some separate work with CNN with another application. And with other student, I said, look, some of this data analytics kernels that I showed you in the first 2 pieces, we have kind of done a lot of work with it. So let's think of something else.
Okay.
And he came up with some computer vision applications, and we finished up working on those. So, because they kind of fit the scenario that your IoT devices are out there with some cameras that are capturing some images. And then you are trying to see, if you have seen certain things in those images. So, one of my colleagues at Ohio State had this application where he would build systems that would try to distinguish between a human walking and an animal walking.
Okay.
And the idea was to put this application on some very low-end devices in a forest and see some illegal poaching activity. So that was, we didn't really finish up doing his application, but that kind of motivated this idea of that computer vision applications. And actually, CNN also, convolution neural networks can also be applied to images. So that's where those things came
from. Okay. Well, thank you so much. I don't think if any other question is coming up. I don't think so.
Okay, yeah, I know. I think Darish and Edward might be in this little, distributed computing thing. So they might have collected a lot of questions for that. That starts in another 10 minutes.
I just knock at your door.
Huh?
They will just knock on your door whenever.
Right. Well, you're welcome to. But thanks for everyone for joining. And
well, thank you.
I know, this is maybe a little different than any of yours background, but hopefully this was somewhat interesting.
No, it was. I learned a lot, and I think it was extremely interesting. It was the right level for me, and I do enjoy your graph too, showing progression. I think that's a good selling point, and it's enjoyable. Okay, well, thank you everyone for joining us. I don't remember who's next. I know somebody's next.
That's okay. I think, Harley will send out his.
Yeah.
Harley has a nice program to send out these reminders at 2 p.m. on Thursday, which go out even if there is no speaker.
Yeah. But so now next week we'll have Omar Chaudhuri speaking about adversarial testing of cellular network protocols. Okay. Well, thank you so much, everybody. See
Okay,
you
bye.
next week or earlier than that. Take care.
Let's see.